exploratory factor analysis and principal components. I'm not spending a whole lot of time on this, and you'll see why in just a moment. So how many of you have had coverage of these topics in previous classes? Get the background. One. Not most people have not. Okay, then that's good because I don't have to unlearn you of anything. I do have more material on this that I'm going to send to you, but I'm waiting for one of the days where we don't have class to be able to give that to you. Speaking of which, that reminds me of something I forgot to say at the very beginning. I posted a video to demonstrate the homework portal. So 3 of your assignments this semester are going to be using that. This is our course website. If you haven't done so already, please follow along with the video and answer the questions to complete homework 0 by next week. You get 3 points extra credit for doing so. That way I know you can use the system and we can troubleshoot any issues before the main homeworks get going. So how many folks have taken the time to do that thus far? Homework 0, we done this? Half of you? Okay, anybody have any problems? No? For those of you who haven't seen this before, what did you think? Thoughts? Nods? I can tell you feedback from previous classes is that there's something very reassuring about seeing the numbers turn green, right? You get the immediate sense of a win. That's what I'm trying to give you. There's so much in graduate school where it's like you can keep going and going and going and you never really like have it be finished. You just have to cut it off at some point. But this is the opposite of that. You have numbers that are correct or incorrect and it will feel good to get them to be green. So yes, so Kayla, thank you. This is why I was reminding of that. There was one question on there that encountered the no class on the syllabus and you counted more than one. I had only one regular class period that is no class because of a conference, which is the 8th of October. This is Thanksgiving week down here, and so the university doesn't have classes, and so I included it to keep the dates consecutive, but I didn't count that. So to me, the correct answer was one class right now where we're scheduled not to meet, and I'll give you more material on EFA and PCA to go over that day instead. So. All right, so that was actually having only that class be missing was why I remembered to talk about this. So here we go. All right, EFA, PCA, what are they for? And this comes back to formative versus reflective, by the way. So this is all circling back to that distinction because these two techniques are very similar, but they're for different purposes. So, all right, hopefully the internet is going to cooperate with all of us. Can you all see this still? Am I still sharing? Good. Okay. Another question. Um, Reading the question, processing. So the question was basically if you have two different constructs, is it necessary or useful to use the same response formats? I think it depends on the constructs. Not everything has to match, right? If you're adding items up and creating a sum, then each item has to contribute into this to the same extent. And that's where it matters. Like you can't add an item that has 5 choices to an item that has 7 choices. But if you free yourself from this idea that you're going to be summing items, then the number of choices for each item and what they are should be tailored to what the item says. Like some items don't need more than 2 choices and some items do. So it's thinking about like what is the best way to capture the differences between people in that behavior or that attitude and then designing the response options with that in mind rather than keeping them matching across all the others. So, all right. So here we are. EFA and PCA. So tons and tons of acronyms in this class. I apologize if I say them without defining them. EFA stands for Exploratory Factor Analysis. That is in contrast with CFA, which is Confirmatory Factor Analysis. Principal Component Analysis is PCA, which is also an exploratory procedure. So both of these procedures, EFA and PCA, are alike in that you basically throw your data at the computer and you let the computer decide what it thinks you're measuring. They're exploratory, and for that reason, I believe not so useful. So back to the bigger picture here. In thinking about whether or not an instrument is good and useful, I think of this in terms of a hierarchy of concerns, where at the highest level of the hierarchy, there's validity, right? Ultimately, are you measuring what you think you are? You have to make an argument based on how scores on your instrument relate to other things, usually to demonstrate validity. It can also be demonstrated by internal evidence with respect to the ordering of the items and the responses. That's something we'll get into later. But it's always a matter of degree, and it always is a matter of how it's being used. So a given instrument is not valid or not, it's valid for a certain purpose in a certain context. That's like the biggest one. But before you can get to validity, you have to have evidence for reliability. Before you can know if you're measuring the right thing, you have to know that you're measuring a thing, right? Internal consistency is the idea for this. So to what extent would you get the same estimate of a latent trait over and over again if you did this measurement procedure multiple times? So I can give you a ready example of this. I'm looking down at my watch. I have a Fitbit. I believe that my Fitbit is reliable, but not necessarily valid. Do you know what I mean? Right? It has some kind of algorithm for trying to predict how many steps I've taken. Even though if I wave my arm, it thinks I'm walking around, right? That's part of the algorithm. And therefore, how many calories I've burned, what my heart rate is, and so forth. I bring this up because I have had a lot less activity since lockdown. I don't know if you guys have experienced the same phenomenon, right? I've gotten more exercise because it's like, okay, it's me time. I need to get out of this house or I'm going to kill somebody. Like I need, some sort of stress relief. So I've gotten much more regular at my exercise, but the rest of the time I'm sitting on the couch or I'm sitting at my desk. I'm sitting, 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 sitting. So lo and behold, I looked at my calorie burn from last Tuesday and Thursday, and it was like 300 calories higher than it should have been. Thanks to you guys. Fitbit thinks that I am burning calories by teaching right now. And I don't know if it's because my heart rate is up relative to when I'm just sitting here, or all of the gesturing and whatnot. It thinks I'm out on a walk. But thank you, because apparently I am going to be losing weight by teaching. Hooray for me. And it's not just talking, because I recorded a bunch of videos on Friday afternoon and I had no extra calories burned. So it's not just teaching, it's teaching to a live audience. So whatever Fitbit is measuring, I don't know. I know it's doing so with the same algorithm. Same thing with my bathroom scale, right? I believe that it is reliable. I have no idea if it's actually valid as a measure of weight, but reliable is good enough because I can see if it goes up or down, and that's the information that I'm looking to refer to collect. But a precursor to reliability, knowing how consistently you've measured something, is knowing that it's only one thing that you're trying to measure, dimensionality. Because it makes no sense to talk about reliability of two things smushed together. If I have a medium score on a trait, and the trait is actually measuring two things, I could get a medium score by being sort of mediocre on both, or I could be low on one and high on the other, and they balance each other out and they create a medium score. Right? The meaning of that score is predicated on the idea that it's measuring a thing. So the extent to which it's measuring one thing is an assessment of dimensionality. Whether it's measuring that one thing consistently is reliability, and whether the one thing that it's being measured is actually the thing it's supposed to be is validity. So it's like validity is at the top, and all of these things have to be in place before we can talk about it. So everything that follows in this lecture is at the bottom level, dimensionality. And these are techniques that were developed starting back in, I'd say 1904, I think is the earliest reference that I know of, that did not have the advantage of high-powered computing. So a lot of these things are based on what they could do with the time, and that's why they're as limited as they are. But ways of assessing dimensionality if you don't have a latent trait model. That's where we're going with this. So this course is dedicated to latent trait models. Um, we get explicit evidence as part of the modeling process for whether or not the pattern of relationship across the items confirms with our predicted model of dimensionality. There should be, chunks of items that are more related if they're measuring the same thing, and items that are less related if they are measuring different things, right? The extent to which our data support our ideas is evidence for dimensionality. So to me, there's a very big difference between the goals of a latent trait measurement model, which are all confirmatory in nature, and what EFA, exploratory factor analysis, and principal components analysis, which is also exploratory, are trying to do. They are trying to guess at dimensionality with no starting point. Like, it's the computer, just you throw your data at it and it spits back what it thinks. And for that reason alone, I do not think these techniques are useful. I do not think you have to start there. I think you get to start at confirmatory if you at least have a clue. And the reason that I think this is because when it boils down to it mathematically, exploratory factor analysis that's using the same method of estimation as confirmatory is a confirmatory model with a series of really uninterpretable constraints. We have the choice of making constraints that are useful and interpretable instead, and that's the way that we're going to go. So my premise is that exploratory techniques are not helpful. That's just my bias, and that's why I'm not spending a lot of time on them. There's a lot of language that goes with this versus exploratory means. What I mean by confirmatory is that as long as you have a clue, right, you know what the items are supposed to measure. You might not have an exact idea of whether it's one thing or two things, but you have a clue, right, as what the possibilities are. You can set up models that embody those clues. You can set up a model that says all of these items measure this one thing, and you can pit it against a model that says, no, these items measure X, but these items measure Y, and you can see which one the data conform to better. And then if you're wrong, which you inevitably will be, right? Maybe it's possible that one of the things that you thought was one trait is actually two. You will get evidence for that, and you can remedy your model to reflect your new belief structure based on your data. So in that sense, it's a mixture of confirmatory and exploratory in the way that you're using it, because you're going back and forth with what the data say versus what you think, which is why it's helpful to have more than one sample. But having a set of techniques that allow you to input, no, this is what I think it should be in the first place. That's confirmatory, and that's going to be more useful than this stuff. But because this is still really prevalent, and because you may run into objections from reviewer 2 or 3 or people on your committee who say, well, you have to start with EFA, I want you to know enough about it to say to them, nah, actually I don't, and here's why. So these two topics are put together into one lecture, which is in and of itself somewhat controversial. There used to be whole sets of journal articles dictated to fights with people about this, whether or not EFA and PCA were similar or different, and people were really entrenched in one view versus another. They are for different reasons, but they share a lot of overlap, which is why I talk about them at the same time. The main thing that I want you to get out of this is the idea that these are not testable models. This is not a process of hypothesis testing in the way that you're used to, where you ask a question, you get evidence, you get some sort of p-value, or you get a credible interval if you're in the world of Bayes, and anyone would look at that same evidence and come to the same conclusion. This is filled with ambiguity, and that is the reason why it's less useful. My thesis is that it's not your data's job to tell you what it's measuring, and if you don't know, game over. Just absolutely from that point. You should at least have a clue, and I'm sure that you all do. Researchers always have a reason why they gave the measures that they gave. So what are these things for? EFA is all about the structure of the responses and how many factors are being measured and which items measure each factor. So understanding the underlying structure is the point. And the underlying structure, the evidence for that, is the patterns of correlations among the items. So most of the time we're dealing with correlation matrices. When you talk about EFA, that's going to switch to covariance matrices when we go to CFA, but it's still the same idea. It's the pattern of association between the items. That's what's giving us some evidence for the underlying structure of the traits. And getting that structure is often the point. So you will see entire articles published with the results of an EFA, and here's what we found, and here's the structure, and ta-da, like that's the point of the article. In contrast, PCA, principal component analysis, is an abbreviation motivated procedure. The goal is to take a whole shit ton of information and summarize it in a way that makes it easier to work with. It's not about an underlying structure. It's about reducing information into fewer pieces and hopefully maintaining some integrity of the information while doing so. So the indicators that go into a component analysis don't have to be related because their correlations aren't the point. Principal component analysis is trying to summarize variances, not covariances. It's trying to abbreviate a set of variables. So I haven't seen a whole lot of PCA in recent literature, with one exception. This tends to be used, I think, relatively frequently in neuroimaging data. So if you have like EKG readings or ERP, event related potentials, as they say, and you have a net that's measuring electrodes, and you have 128 locations measured for, say, 100 trials, and each trial lasts several seconds, and you've got millisecond level precision, right? I'm not being egregious here. Like that's literally what you have for these sorts of studies. You don't have a lot of people, but you've got a ton of data. PCA is often used in that context to try and summarize these signals into fewer pieces. So you might have something like, the right hemisphere and the left hemisphere, and like the sections of your head that are supposed to be activated, right? There's my neuroscience. I got a B in neuroscience and I'm proud of it. Sections of the head is the best I have for you. But true neuroscientists would be like, yeah, I know what you're talking about. There's areas of activation. And so you may have a component that's meant, for this area versus that area. You're trying to summarize information so that you don't have to deal with 8,000 data points. PCA is a method with which to do that. So advice to starting a factor analytic study: having more than one trait, having enough good indicators of a trait, and having a big enough sample to do everything. There's all kinds of rules of thumb that people use in factor analysis, like you should have at least 5 people per indicator. Those rules are not one size fits all. It always depends on how good your indicators are. The better they are, the more you can get away with in terms of smaller samples. The process tends to go like this. So we would choose an extraction method or an estimation method more generally. Let it pick how many factors, decide amongst rotations, interpretation. This is often an iterative process. And then you may be tempted to generate factor scores at the very end of this. Don't do that. So the school of thought then, I'm talking about both PCA and EFA sort of lumped together at this point. The big difference between them is what data is going to go into this analysis, whether it's the full correlation matrix or some sort of reduced version. PCA, it's the full one. It's all the variance in the indicators goes in, and so all of the variability in each indicator is up for grab. In EFA, it's the common variance that goes in. The logic is that any one indicator, if it's measuring some latent trait, then it should be related to the other indicators. So it can only measure the trait to the extent that it has these relationships. So what goes on the diagonal where the variance would be is the variance that's in common with the other indicators. How much of the common variance that we have. And the term for that is a commonality. It's labeled as h squared. Sometimes you'll see it as r squared and other times. So the big difference here is that any of the variance that's idiosyncratic to a given response variable is dropped ahead of time in EFA, but it's kept in PCA. PCA is a model that is formative. The trait, called a component, is the outcome. So you will perfectly reproduce any correlation matrix, it's the full one with all the variants, if you have as many components as you have responses. So if I had 5 indicators, a component analysis would be fitting models that looks like this. Component 1 is a weighted combination of each of my indicators where the weight is being estimated as part of this process. Component 2 picks up whatever component 1 didn't get. Component 3 picks up whatever 1 and 2 didn't get, and so forth, all the way up to 5. If you had 5, it would perfectly reproduce all of the information that was in your original 5 indicators. People typically wouldn't bother to do that. The question then is, how many of these is enough? How many components captures most of the information in these variables to where you feel good enough throwing the rest of them away? But note the direction. C is the outcome, C is the component. It is a weighted combination of the indicators, and there's no error term here. So the trait, so to speak, is the outcome. The indicators are like the predictors in this case. So let's say that we have data that look like this. We have 4 indicators. They have a correlation matrix that indicates that there's probably 2 things going on here because items 1 and 2 are more related and items 3 and 4 are more related. So it's not that whatever's being measured by 1 and 2 has nothing to do with whatever's measured by 3 and 4 because they do have these cross correlations, but it looks like there's 2 things. So based on this visual pattern, you might anticipate that a component analysis would look something like this, where I've got one component for the red items, and I've got another component for the blue items. Question, loadings. The question was, what do loadings mean here? They're weights. How much of indicator 1 do I need to put into component 1? How much of indicator 2 do I need to put into component 1? And the weights are being estimated as part of the process. Thanks for the question. Okay, so based on this correlation pattern, you might think that I would end up with 2 components and that they would be formed this way. But that is not what PCA does. That's not what it's for. That's what EFA is for. The role of PCA is to summarize information. So what it would end up looking like, this correlation matrix could be summarized by the first component, the one that's going to capture the most information, would be something like this, where the weights for items 1 and 2 would be 0.5, the weights for items 3 and 4 would be 0.4, and because these were more highly related, we take out more of them. So component 1 is trying to summarize as much information out of these 4 indicators as possible. So it's getting all of them. So what's left? Well, the next component is trying to capture whatever information isn't already captured by component 1. So it would look something like this. So all of these still contribute, but now we're trying to kind of pull them apart. What's not in common is being emphasized by the difference between the loadings. And the question that I would have for you is, what the hell do I do with that? Right? How do I talk about this? Because at the end of the day, if you're trying to create components, they're to put them in another analysis, right? These are abbreviations of groups of variables. So how do I use a 1-unit change language, right, to think about this as an X or a Y in a further analysis when this is the way that it gets made? It's very tricky. So component analysis is not about finding groups of indicators, it's about summarizing information. And because of that, you can get some weird patterns that are not readily interpretable because it's not trying to interpret them. It's just trying to capture as much stuff as possible. So in this field, you will come across some other vocabulary where you'll get a matrix that looks like this, where down the rows are the indicators, across the columns are the components. So let's say that we do this analysis, we decide that we're going to keep 2 components. How we decide that, I'll get to in a minute, but let's just say we decided on 2. The values inside this table are the loadings that correspond to each component for each item. If you go down a column, if you square and then sum, the values in this, you end up with something called an eigenvalue. You can think of an eigenvalue as how much information you have captured out of all of the indicators. So we're dealing with a correlation matrix. That means each indicator has a variance of 1. So the most you can have is 4. How much did we get? 1.21 out of 4. That's like 30% of the information. So of a total variance of 4, our first component got 30% of it. And we can do the same thing to figure out how much the second component got under the belief, as they currently are, that these two things are unrelated. So component 2 picks up where component 1 left off. If you go across the rows, you get to what ends up being the variable's communality. How much of it is being represented by the component solution? So for instance, for the first indicator, if I have this loading squared plus the next loading squared, I get to 0.68. So out of that first indicator's total variance, which is 1, the two components have captured 68% of it. And I can do the same thing for each row. So my question for you then, if you were looking at this, is that good enough? Do you think 68% of a variable is good enough? That you wouldn't feel bad about throwing away the other 32%? What do you think? Could reasonable people disagree on this point? How much is good enough? Yeah. Do you see any standard errors or anything like that on this page? Nope. They don't come with it. People have figured out ways to get standard errors since then, but the default packages, when you run this, say, in SPSS or SAS or R or what have you, you don't get standard errors. You just get these numbers. And so you're deciding how many components you need and whether or not that's sufficient to meet your purposes. How many components you need is supposed to be related to how many things you're measuring, but that's not what this is trying to do. So this process you would do in both EFA and PCA. There are different ways of finding those loadings. There are procedures that try to maximize the commonality, the amount of variance that's being accounted for across the components. Those don't have assumptions about the distributions of the indicators. They're just based on properties of matrix algebra. You get eigenvalues and eigenvectors and all that kind of crap that you may have learned at some point that I never learned very well, to be honest with you. Or you can use maximum likelihood. So within EFA specifically, you can use maximum likelihood. That's not an option in PCA. And if you're going to go down the route of confirmatory models, you use maximum likelihood on those as well. And so it's most internally consistent to use maximum likelihood throughout the same thing. And that's the point at which I would question the utility of EFA. Because it turns out that EFA is CFA with just a bunch of stupid constraints and extra stuff in it that you don't need. So that is foreshadowing what's going to happen. So formative is what CFA is doing, reflective is what EFA is doing, and I've got some stuff on that coming up. So, but that's probably a good place to stop for today. So questions or comments from you guys? Okay, so big picture, these techniques are designed to provide evidence for dimensionality, and one of them is trying to find patterns of correlation that are measuring factors, and the other is simply trying to summarize variables and account for their variance. PCA is the latter and EFA is the former. Question, is there a difference between subdimensions and multiple dimensions? Not to me. I see that as a semantic distinction. Oftentimes, when someone is developing a new measure, they might think of it as sort of one overarching construct and then have like different aspects of that construct as either subscales or subdimensions. That is a multidimensional measure. The extent to which each of the items measure the subdomain they're supposed to, and then the extent to which the pattern of correlation among the subdomains is itself consistent with a higher order domain, those are all empirical questions. But that's multidimensional measurement if you're talking about measuring more than one thing at a time. All right, other questions? Okay, then it is Tuesday, which means don't have a good weekend yet. But do please take care of yourselves and stay safe. Please stay in your houses or your apartments, and if you have to leave, please put your masks on and be careful. It's very dangerous out there, okay? I want to see everybody back and healthy next time if possible. So have a good day, guys. Let me know if you need anything. Otherwise, I'll see you Thursday.